Hello everyone, this is Mirzai from Cal Poly Pomona, and in this lesson we are going to cover the assignment problems and Hungarian method to solve the assignment problem. What is the assignment problem? A special cost of transportation problem is called assignment problem that has three special conditions. If you are not familiar with the transportation problem, please refer to the video related to the transportation problems. So the first difference of transportation problem and assignment problem is that the supply and demand are the same and they are equal to 1. In the context of operations research 1, we just deal with the square matrices, and later on we introduced non-squared matrices and conditions. So for now we are just focused on the cases that you have a squared matrix for assignments. The second difference between the assignment problem and transportation problem is that all the decision variables in this case are binary variables, meaning that they only take the value of 0 or 1. If you remember, you didn't have this condition in the transportation problem and your x's were real numbers. The third condition is that all the constraints are in the form of equations. In your transportation problem, for the supply constraint, you had less than or equal, and for demand constraint, you had greater than or equal signs. But in this case, all the constraints are going to be in the form of equal sign. So these are the three main differences between the transportation and assignment problem. Let's look at one example and see how we formulate an assignment problem, and after that we explain the Hungarian method. So in a construction site there are 4 cranes. Each crane must be allocated to a job, and the time required to set up each crane for each job is shown in the table here. The question is, find the best assignment of cranes to jobs so that total time required for completing the jobs is minimized. So basically we want to allocate exactly 1 crane to each job, and each job must be exactly allocated to 1 crane, not more. And we want to do it in a way that our total cost is minimized. So in this case, our decision variables are binary because we're trying to decide whether to allocate a crane to a job or not. So if I define all the decision variables here, which are 16 decision variables, I'm trying to understand whether the value should be 1. If it's 1, then it means that I make the allocation. Otherwise, I don't make that allocation, and your x takes a value of 0. So for example, if x11 is the allocation that I try to do, allocating crane 1 to job 1, if it takes a value of 1, it's going to cost me $16. So therefore, I have to pay $16 for allocation of crane 1 to the job site 1. So if I want to define my total objective function, I can define it in here, basically multiplying the cost coefficient to each decision variable. And if that decision variable takes the value of 1, then the cost associated with that gets activated. In the end, we just want 4 of these decision variables to become 1, because for each crane and each job, we exactly want 1 allocation. So we have to make sure that for each row, we only have 1 decision variable that is equal to 1. So I write the constraints regarding the cranes. So for each crane, we want to exactly allocate it to 1 job site for crane 1, 2, 3, and 4. Also, for each job, I have to make sure that I'm not allocating it to more than 1 crane. So for each column, also, I have to write 1 equation and enforce that one of those x's in each column becomes 1. You can think about it like a Sudoku game. So you're trying to put 4, 1 in this table so that each row and each column, the summation is exactly equal to 1. And also, you have to mention in the end that all the x's are binary. If you make that allocation, the x is 1, otherwise it's 0. Now, how we can solve this problem? Since all the x's are binary variables, we haven't covered a method so far that you can solve this problem. One method to solve this problem is called Hungarian method. Let's learn Hungarian method using an example. This is a table of the cost for crane to job allocation. This is not similar to the one that you saw earlier. This is a different example for certain reasons. So suppose that you're trying to find the best allocation of cranes to jobs, and the numbers inside the table is the time that takes for you to do the setup. And therefore you're trying to minimize the setup time, so it's a minimization problem. The way that Hungarian method works is first by finding the minimum of each row and subtracting it from the values in that row. So first let's find the minimum of each row. As shown on the screen, the first row minimum is 2, the second row is 3, third row is 4, and the fourth row is 3. Now we subtract this minimum value from all the rows and we get to this new table. The next step is to find the minimum of each column and then subtract that minimum from each column. So for each column I wrote the minimum value and now subtract that minimum from each column in the next table. And this is what I get. So far what we did, we found the minimum of each row and subtracted from the associated row. Then we found the minimum of each column and subtracted that value from each column. The third step is to find the minimum number of vertical or horizontal lines that we need to cover all the zeros in the matrix. The way that you lay out those lines does not matter. The most important thing is to use the minimum number of lines to cover those zeros. And your lines cannot be diagonal, it should be vertical or horizontal. So the way that I lay out my lines is this way, but you can choose an alternative way, but you have to make sure that you are using the minimum number of lines required. I'm going to take this to the next slide and continue here. So this is what we have gotten so far. Now what? So if the minimum number of lines required to cover all the zeros is not equal to the dimension of your matrix, which is 4, then you haven't reached the optimal allocation yet. So the dimension of your matrix is 4 by 4. So your M representing your dimension is 4. So the minimum number of lines is 3. What you need to do is to go to the next step. If the minimum number of lines was equal to 4, then you had reached the optimal solution and each zero would show you a possible allocation. But since we haven't reached to that point, we continue to the next step. In this step, we have to find the minimum of uncovered value and then subtract that minimum from all the uncovered value and add it to the corner points. And from corner points, I mean the intersection points, wherever your lines are intersecting. So if I do this step, I find the minimum of uncovered value, in this case is 3. I subtract that from all the uncovered values, which is the values that is in the next table you see by kind of dark brown. And now I have to add it to the corner points or intersection points, which are 6 and 1. So if I add 3 to those intersection points, I get 9 and 4. The rest of the points are remained untouched. I don't do anything with the rest of the values and copy them as they are in the new table. So find the minimum of uncovered value, adding them to the corner points, and subtracting them from the uncovered value. So that's the step that we implemented. Now we go back to the third step, try to find the minimum number of lines that we need to cover all the zeros. In this case, again, with 3 lines, I can cover all the zeros. So 3 is not equal to 4. So I have to continue and redo this step number 4. So we went back to the step 3. 3 is not equal to 4. We go back. I'm taking this to a new slide. And as you saw, this is the final table we had. Now I have to find the minimum of uncovered value, which is equal to 1, subtract it from uncovered value, add it to the intersection point, and copy the rest of the table as they are. So I'm implementing these steps. I deduct 1 from all the uncovered value, add it to the intersection points, and copy the rest of the table as they are. Now I have to find the minimum number of lines I need to cover all the zeros. In this case, I need at least 4 lines to cover all the zeros. Therefore, 4 is equal to the dimension of my matrix, which was 4, and therefore I'm in the final optimal table of assignment problem. Now, how I make the assignment, each zero in the final table shows a possible allocation. But you have to be very careful the way that you make these allocation. For example, if I choose this allocation, it means that crane 4 cannot be allocated to job 2 anymore. So I have to make sure I pick the zeros in a way that each job and each crane has exactly 1 allocation. So one systematic way to find the allocations using the zeros that are in the final table is to start the assignment from the row or column that has the minimum number of zeros, because those are the one with the lowest option. So the way that I deal with this is I start writing all the number of zeros in each row and each column. For example, in the first row I have 2 zeros. In the second row I have 2 zeros. And in the last row, for example, I have 3 zeros. Then I start allocation by allocating the row and column that has the lowest number of possible options. So a lot of rows and columns have 2 options, so you can pick one arbitrary. What I pick is the first allocation of crane 1 to job 1. With this, I cannot put any other allocation in this row and column, therefore I eliminate them. And I have to also update the number of zeros in the remaining table. Now there are 2 numbers that are updated because these zeros are eliminated from the table. Now everything has 2 options, so I pick another one randomly and make the allocation and eliminate the row and column related to that allocation. Now I have to update the number of zeros in each row and each column. Now as you see, there is a row and column with only one possible allocation. So I pick this column because it only has one allocation. I make the allocation there and then eliminate that, and I'm left with only this allocation. So this becomes the final allocation of cranes to jobs. Now this is the final solution that we found. Our final solution is x11, x21, x34, and x43 have a value of 1, and therefore the costs associated with these are going to be activated in my objective function. If I go back to the original cost table I can pick the costs associated with those allocation and calculate my final objective function value. So as you see, my final objective function value in this case is equal to 19 by finding the costs associated with those allocations that I've made in this case. With this, our lesson regarding assignment problem and Hungarian method has concluded. Thank you for watching.